Okay, so 2.4, we're going to look more closely at experimental design. Usually we do this over 2 days. I'm just going to make one video for both days. You can just fast forward to where we left off if you're looking for day 2. So with experimental design, we're going to look really what are the 4 big basic ideas with an experiment. Yesterday we sort of looked at the generic, like randomly select your units, randomly impose or randomly assign your treatments, and then measure your response variable. So suppose we wanted to design an experiment to see caffeine and see how it affects pulse rate. What's our explanatory variable here? So remember, your explanatory variable is what you're going to manipulate, and that's the caffeine. So we're manipulating that. What's the response variable? What are we going to measure? We're going to measure the pulse rate, probably the change in pulse rate. So this is what you're going to measure at the end. Our experimental units, for now they're just going to be people, because we're going to give them. So here's my initial plan. I'm going to measure everyone's initial pulse rate, give each student some sort of caffeine, wait, measure their final pulse rate, and compare. So if I'm just looking at that, there are obviously a couple problems with this plan. If I gave everybody some sort of caffeine, I would want to make sure here there's no control group. Maybe there's some outside factor that might affect pulse rate, like making sure to not do this like before a fire drill or after a fire drill. Also, we don't know, like, is anybody moving around? During the wait time, are we just making them sit there? Are we going to go make them run a lap? Like, what are we going to do? With the caffeine, there are no levels. Am I giving everybody the same amount of caffeine? Am I giving everybody a little bit of caffeine? Also, you need to be careful, because usually with caffeine, we end up having some sort of sugar. So sugar could be a confounding variable here, depending on what kind of caffeine I'm giving my subjects. So there's a couple problems. So let's go through more specifically, how could we create almost like a better plan? Okay, so I'm going to kind of go through these again on the next page, but obviously we would do that as a class. So some problems can easily be solved by just adding a control group, which does not receive any caffeine at all. In our experiment, we can accomplish this by using 2 levels of caffeine, either no caffeine or some kind of caffeine. For example, we would assign each member of one of two treatments: regular Coke or caffeine-free Coke. Why don't we give Coke to one group and nothing to the other group? Well, we want to make sure that we have the same amount of sugar, right? So that sugar is not a confounding variable. Also, we'll talk about in a second the placebo effect, making sure like that everybody gets at least something. So maybe there's a placebo effect. We'll get into that in a second. Oftentimes, applying any treatment can create a change in the response variable. For example, when a child gets hurt, they feel better when their wound is kissed or covered with Band-Aid, even though neither of those treatments actually take away the pain. In our study, if only one group got a treatment, the fact that they were chosen to receive free soda might make their pulse increase before the caffeine even hits their bloodstream. So again, this is called the placebo effect. So the placebo effect occurs when subjects in an experiment know they are receiving a treatment. This knowledge may cause a change in the response variable, which will confounds the effects of the treatment. In other words, we will not know which caused the change in the response variable, the explanatory variable or the placebo effect. Having every subject receive a treatment ensures that the placebo effect will treat both groups the same. Then, any difference in their pulse rates can be attributed to the treatment again, which is the caffeine, and not the excitement of just being in an experiment. Of course, it's essential that the subjects do not know which treatment they are receiving. When a person does not know who is receiving the treatment, this person is blind. So there are two classes of individuals who can influence the results of an experiment. Those who could influence the results, so the subjects, the treatment administrators, they're all in one group. And those who evaluate the results, those are in a separate group. Think about, usually when you're doing this, it's a company. So the company is like a third group. They know which treatment is which. Those who evaluate the results may just have soda A, soda B. And they give their results to the company, and they can still be blind. So the treatment administrators and sometimes those who evaluate may end up being the same people, but they're at different spots within the experiment. So when every individual in one of these classes is blinded, we call that a single blind. If every individual in both classes is blinded, then we say it's double blind. Okay, can we run our experiment in a double blind way? Yes. Because you could, like I said, you could have soda A, soda B for everybody. Now there's some experiments that cannot be blind at all. Or double blind, I guess. We talked the other day about the frog anatomy. The person who is actually the subjects will know whether that they are dissecting a frog, physically, versus using a computer. So that would only be single blind. It could just say dissection program A, dissection program B, but it definitely would only have to be single blind. There's no way you can double blind that. Other ways you can't double blind is if, like I said, you have having them do something physical, like different workout routines or different sleep routines. They obviously know what treatment they're getting. Okay, so here we have on the next page 4 key principles of a good experiment. So we're going to go through all 4. Make sure you know these. A lot of this stuff you'll end up seeing kind of as we go through it. It kind of makes sense. So our goal when designing an experiment is to make treatment groups as similar as possible with the exception of the treatments. Then if there's a change in the response, it can be attributed to the explanatory variable and not any other extraneous variables. So an extraneous variable is one that is not of interest in the current study but is thought to affect the response variable. For example, sugar is an extraneous variable since it may affect pulse rate. If one treatment group was given caffeine-free Diet Coke, then sugar and caffeine would be confounded. There is a difference in the average pulse rate of the two groups after receiving the treatments. We wouldn't know which variable caused the change and to what extent. To prevent sugar from becoming oh my gosh, I can't spell. A confounding variable, we need to make sure both treatment groups get the same amount of the treatment. So confounding variable and extraneous variable are pretty much the same vocab. We just use them kind of interchangeably. So we need to be careful about that. So principle number 1 of a good experiment is direct control. What that means is you hold all the extraneous variables constant for all treatment groups so that their effects are not confounded with the explanatory variable. If we do not control these extraneous variables by making them the same for all groups, they could confound the effects of caffeine on pulse rate. For example, we may not be able to tell if it was the caffeine or the sugar. So we want to be in control of the experiment. This doesn't necessarily mean that we have a control group. That we'll get into differently. But direct control means that you are trying to hold all the other extraneous variables constant and just manipulating your explanatory variable. So, principle number 2, this is a big one. Number 1 is not that bad, but number 2 is usually the bigger one. And that is called blocking. So blocking is when the subjects are divided into groups or blocks based on some extraneous variable and then separated into different treatment groups. So What if men react differently to caffeine than women? How can we eliminate this potential confounding variable? So what we would end up doing is we'd group men together, and you have your control group in your treatment, and then we'd group women together. And then you have your control in your treatment. So blocking in experiments is similar to stratification in sampling. So I like to explain to people blocking and stratification come at two different points within your experiment. Stratifying is at the beginning when you're getting all your volunteers or whoever. You're stratifying them. You're putting them into groups. Blocking comes after you have them. The blocks don't necessarily have to be the same size, and they don't necessarily have to represent the whole population like strata do. So let's say you had 60 volunteers for this experiment. Like if I took this class, I have 35 students. Let's say I had 15 guys and 20 girls. I would group the guys together, group the girls together. That's the blocking. Stratifying would be if I went to all PSEP AP Stat students and grabbed a certain amount of guys and a certain amount of girls. So they come in different parts of the experiment. What blocking does, it reduces the variability of the results, just like stratifying. Blocks should be chosen like strata. The units of the block should be as similar as possible. You should only block, though, when you expect that subjects in one block will have a different response than subjects in the other block. If you think that it doesn't matter, don't worry about it. Don't block. Blocks are obviously chosen subjectively, based on the extraneous variable. Then we can randomly assign treatments to the subjects within each block. Two blocks that are the most common is that we'll block on age or gender. Those are obviously the most common. Okay. All right. There are different types of blocking. So one example of blocking is called a matched pair. So a matched pair is a block of size 2. It consists of a pair of similar subjects. Treatments are randomly assigned within each pair, and the experimenter records the difference in the effects of the treatment for each pair. So like if we were looking at pulse rate and caffeine, a completely randomized experiment, I'd randomly assign half the students to caffeine and the other half to no caffeine. Measure each person's pulse rate and compare the change. So that's just basic. If I were to block, I assume there's a difference in the effects of caffeine on males and females. Assign all males to one block, all females to the other block. Randomly assign half the males caffeine, half no. Do the same for females, run the experiment, and measure the change. Now for matched pair, I could order the males from lowest to highest with the initial pulse rate, then pair them up, do the same for females. Take the first pair of males and randomly assign caffeine to one and the other one to receive no caffeine. Repeat the process for all the pairs of males and females. Perform the test and then measure the change. Matched pairs repeated. You can be a matched pair with yourself. So randomly assign half the students caffeine, the other half no caffeine. Measure the change in their pulse rate, then the next day do the test again, but switch. Those who received caffeine the first day received no caffeine. So this is a matched pair. What you're doing here is you're comparing with yourself, which is kind of nice because you know your initial resting pulse rate anyway, so it would be easier to compare. So you can be a matched pair with yourself. Now, this is usually the end of day 1, and we get into randomization and replication tomorrow. I'm going to continue the video. If you missed just day 1 of the notes, stop here. If you missed day 2, start here. So the third principle is randomization. I've sort of been talking about it a lot as we've been going through this. It's the random assignment of subjects to treatments to ensure that the experiment doesn't systematically favor one treatment over the other. Basically what we try to do is we try to average out the effects of the extraneous variables on the responses. So if we randomly assign subjects to treatments, this should control but not eliminate the effects of these variables, since their effects should be spread equally between the two treatment groups. So we always want random assignment. We must always randomize, since there will always be extraneous variables we just don't consider. If each experimental unit was to receive only one treatment, then which treatment unit receives which treatment should be determined randomly. Use one of the randomization methods, such as a random number generator or random number table. So, if each treatment is supposed to receive all treatments, then the order should be determined randomly for each experimental unit. So all students will receive caffeine and no caffeine, but the order will differ for each student. So how do we randomize? It's very, very similar to how we sample. The easiest one, especially if there's two groups, is to flip a coin. So this is easy when you have two groups of people. Heads, this happens. Tails, this happens. Because when we start writing out our experimental design, you have to be specific. So flipping a coin is the easiest. We can use a random number table, a random number generator, or you can do slips of paper. These are all good for 3 or more groups. Okay, obviously I can't flip a coin when I have 3 groups. So we'll kind of go through these more, like I said, when we start writing them out tomorrow, but these are the most common. Excuse me. Okay, the last principle is replication. And it actually means 2 things. It means ensuring that there's an adequate number of observations in each treatment group, and that we can keep doing this experiment over and over again. So if each treatment group only had one experimental unit, then we would not be able to conclude that any changes in the response are due to the treatments. It's also possible that some characteristic of the unit was the cause of the change. So what we do is we want to increase the sample size. If we increase the sample size, that makes randomization more effective. The more subjects we have, the more balanced our treatment groups. For example, if we will have 10 subjects and only 2 have a certain unknown characteristic, it's quite likely that both of these subjects will end up in the same treatment group simply by chance. If you were flipping a coin and wanted to get as close as possible to 50%, you would decide to flip a coin more than a few times. So, replication also refers to repeating the experiment with different subjects. This can help us feel more confident in applying the results of our experiment to a population. So I want to have a decent sample size with replication, but I also want to be able to do the experiment in more than just one group. So like if I'm looking at high school seniors, I'm not just going to go to Plymouth, Salem, and Canton. I need to go to Livonia and go to Dearborn so that I can generalize to all high school seniors feel this way, or high school seniors in Metro Detroit feel this way. So it's not just one sample size, it's all of the sample sizes. So here's kind of our summary of 2.4. With control, blocking, randomization, and replication, each treatment group should be nearly identical, and the effects of the extraneous variables should be the same in each group. Now, if changes in the explanatory variable are associated with the changes in the response variable, we can conclude that this is a cause and effect relationship. So all we're doing is trying to get a good experiment so that at the end we can say caffeine does affect your pulse rate. So, like I said, this is a lot, which is why we do this sort of over 2 days. But we'll keep going over this. Tomorrow, or in 2.5, we'll actually start designing some experiments. So this section was really just, can you get the key understandings of what a good experiment was? 2.5 will actually start writing them out.